There are various types of vehicles, and they all perform the same basic actions: driving, turning, and stopping. In all of these actions, the suspension system plays an important role in ensuring a comfortable ride and driving stability. Here is a look at the construction of suspension systems and the various types. This video introduction to suspension systems is in two parts. Basic knowledge is the first, and inspection and maintenance is the second. The first video explains how a suspension system functions. It looks at springs, shock absorbers, and stabilizers as components of a suspension system, covering their functions and types. It will also cover different types of suspension systems. The suspension's first function is to transmit the driving force generated by the driving wheels, as well as the braking force generated by each wheel, to the body, while maintaining the proper position of the axle. Its second function is to absorb the shocks and jolts received from the road surface to make the ride more comfortable. The third function is to stabilize the vehicle during driving by ensuring that the wheels follow irregularities in the road surface at all times to improve steering stability. But these functions conflict with each other. For example, if a soft spring is used to improve the riding comfort, steering stability will be reduced. And if a hard spring is used to improve steering stability, the ride will be uncomfortable. It is important to balance these conditions so that the suspension system matches the characteristics of the vehicle. The relationship between unsprung and sprung weight also affects riding comfort and steering stability. Let's suppose that you grab the car body and raise it up. The wheels, axles, and brake system hang down. The weight of these components is called the unsprung weight. The weight of the other components, including the body, is called the sprung weight. Here is a demonstration to show how the relationship between the unsprung weight and sprung weight affects riding comfort and steering stability. As you can see, when the sprung weight is large, the tendency of the body to be jolted decreases, even if there is a bump on the road surface. So a large and heavy body ensures a more comfortable ride. When the unsprung weight is small, the wheels respond quickly to irregularities in the road surface, hold the road better, and thus help to improve steering stability. Using aluminum wheels is one way to reduce the unsprung weight and improve steering stability. Let's take a look at the kinds of jolting and shaking which occur in an actual vehicle. The first is pitching. When the vehicle goes over large bumps in the road surface, or when driving on a rough track, the front and back of the vehicle move up and down in opposite directions. The passenger feels this as a tipping back and forth. Rolling is when the body rolls to the side during a turn or while driving along a bumpy road. Bouncing is the up and down shaking of the entire body when driving along an undulating road. It often happens when the springs are soft. In yawing, the The front and back of the vehicle move sideways in opposite directions when the vehicle goes over large bumps in the road surface or when driving on a rough track. The passenger feels this as a sideways shaking. Apart from these, the wheels and axles suffer types of jolting related to the unsprung weight, called hopping, tramping, and wind-up. Hopping is the bouncing of the driving wheels when the vehicle is started and stopped abruptly. Tramping is the up and down jolting in opposite directions of the left and right wheels. This is most common in vehicles with rigid axle suspension. Wind-up occurs in vehicles with leaf spring suspension. The leaf springs attempt to wind themselves around the axle due to the acceleration and braking torque. The spring's flexure changes at the front and the back, causing jolting. A number of features can be implemented in suspension systems to suppress this jolting in the vehicle, thus improving riding comfort and steering stability. There are various types of suspensions. Here, let's take the double wishbone type as an example to look at suspension components. The spring dampens the shocks received from the road surface. The shock absorber improves riding comfort by restricting the free oscillation of the spring. The stabilizer prevents the vehicle from rolling, and the suspension arm holds the wheels in the proper position. The suspension arm restricts the lengthwise and sideways movements against forces applied from various directions to the wheels, but its construction allows up and down movement. In this case, the suspension arm is separated into upper and lower arms. Now let's take a close look at the functions and construction of each component. First is the spring. The springs of a vehicle use the principle of elasticity to cushion the vehicle body and passengers from shocks caused by the road surface. Various types of springs are used for the suspension, but coil springs, like these, are the most commonly used. Coil springs are made from the rods of special spring steel formed into the shape of a coil. When a load is placed on a coil spring, the entire rod is twisted as the spring contracts. In this way, the energy of the external force is absorbed. Leaf springs use the bending elasticity of steel plates. They are made of several slightly curved, long and short steel plates stacked together. The larger the number of steel plates, the greater the load they can support. For this reason, leaf springs are mainly used on commercial vehicles. A torsion bar spring is a special spring steel rod that uses its torsional elasticity to resist twisting. While coil springs are made from rods of special spring steel formed into the shape of a coil, torsion bar springs are made from straight rods. One end of the torsion bar is anchored to the frame or to another structural part of the body, and the other end to the suspension arm. Torsion bar springs have a simple construction and are compact. For this reason, torsion bar springs are often used in one-box type vehicles. Air springs have the characteristics of air in their elasticity or springiness when they are compressed. Air springs provide optimum riding comfort because the air pressure can be adjusted according to the load applied to the vehicle. But the devices for controlling air pressure, such as compressors, are necessary, so the number of components increases and the suspension becomes complex. Rubber springs using rubber's inherent elasticity are used mainly as auxiliary springs for spring bumpers and other suspension components. While springs act as cushions to absorb shocks received from the road surface, shock absorbers control the oscillation of the springs and enhance riding comfort. When springs compress and expand, the up and down oscillation caused by their rebounding does not stop immediately. This leads to handling instability and also causes an uncomfortable ride. Shock absorbers provide just enough resistance to the up and down movement of the suspension to reduce this oscillation. This graph shows the oscillation patterns with and without shock absorbers installed. As you can see, shock absorbers dampen oscillation quickly and improve riding comfort and steering stability. Let's take a look at the operating principle of shock absorbers. When a piston with a small hole is moved inside a fluid-filled cylinder, the fluid is forced through the orifice. The flow resistance generates damping force and dampens the oscillation of the spring. The various types of shock absorbers are classified according to their operation, construction, and working medium. By operation, single and multiple action types. By construction, twin and monotube types, and by working medium, hydraulic and gas-filled types. First, let's take a look at the difference between the single action and multiple action types. Single action shock absorbers generate damping force only when extended. No damping force is generated when the shock absorber is compressed and the valve is wide open. The multiple action type, on the other hand, generates damping force both when extended and compressed. The valve increases damping force when the shock absorber is extended. Generally, the orifice used when this type is extended is larger than that used when compressed. Most of the shock absorbers currently in use are this multiple action type. Let's take a close look at a multiple action twin tube hydraulic shock absorber. The twin tube type is a double layered tube with a piston that moves up and down in the inner cylinder. The piston is fitted with a piston valve, which generates damping force when the shock absorber is extended. When the shock absorber is compressed, damping force is generated in the base of the cylinder by a base valve. The inside of the cylinder is filled with absorber fluid. Only 2/3 of the reservoir chamber located between the cylinder and the outer tube is filled with fluid. The rest is filled with air at atmospheric pressure. When bounding causes the spring to compress, the piston rod moves downward, increasing the pressure in the chamber under the piston. The fluid pushes up the non-return valve of the piston and flows into the chamber above. At the same time, the amount of fluid equal in volume to that displaced by the piston rod when pushed into the cylinder pushes open the base valve, flows into the reservoir chamber, and damping force is generated by the flow resistance. When the piston rod moves upward due to rebounding, the pressure in the chamber above the piston increases. The fluid pushes open the piston valve, flows into the chamber below, and generates a damping force. At the same time, the amount of fluid equal in volume to that vacated by the piston rod when pulled out of the cylinder pushes open the non-return valve of the base valve and flows from the reservoir chamber into the chamber under the piston. There are orifices in both the piston and base valves which allow fluid to flow at all times. If the speed of the piston rod is low, this mechanism allows the flow to generate a slight damping force with the piston valve and the base valve closed. Next, let's take a look at a multiple action twin-tube gas-filled shock absorber. As explained earlier, in a non-gas type absorber, the reservoir tank is filled with air at atmospheric pressure, which is in contact with the fluid. So when the shock absorber moves quite violently, air is forced into the fluid, causing aeration, or air pockets form in low-pressure areas, causing cavitation. This lowers the damping force of the absorber. When the air pockets collapse, noise is generated. In gas-filled shock absorbers, air is replaced by nitrogen, which applies pressure to the fluid and prevents this from happening. Gas-filled shock absorbers are constructed and operated in basically the same way as the hydraulic type, but cavitation and aeration are suppressed because the fluid is subjected to gas pressure. In this way, a more stable damping force can be obtained. In the multiple action monotube shock absorber, the base of the cylinder is filled with high pressure nitrogen gas. This du-carbon shock absorber is the most typical type of monotube shock absorber. Inside the cylinder, a free piston moves up and down restricted. A storage chamber filled with high pressurized gas is fitted under this piston. The fluid and the high pressurized gas are completely separated by the free piston. During operation, when the spring compresses due to bounding, the piston moves downward. This causes the fluid under the piston to push open the valve and flow into the upper chamber, generating damping force. During the compression stroke, the gas exerts great pressure on the fluid under the piston, forcing it to flow quickly and smoothly into the upper chamber. This ensures a stable damping force. When the piston moves upward due to rebounding, the fluid above the piston pushes open the valve and flows into the lower chamber, generating damping force. During the expansion stroke, the gas pressure pushes the free piston upward for a distance equivalent to the volume of fluid displaced by the piston rod as it moves out of the cylinder. In this way, the free piston applies pressure to the fluid. In this type of shock absorber, pressure from the high pressurized gas is always applied to the fluid. The pressure will not drop, even if the fluid flows at high speed, so cavitation does not occur. Aeration can also be prevented because the fluid and gas are completely separated. Next, let's take a look at stabilizers, which reduce the rolling of the body during cornering. When the vehicle takes a curve, the body leans toward the outside of the curve because of the centrifugal force. If the body leans too much, riding comfort will be reduced and the wheels will lose contact with the road surface, making the vehicle unstable. Independent suspension is particularly prone to such problems. The stabilizer bar is installed not only to reduce the vehicle's leaning caused by centrifugal force, but also to improve the driving force of the wheels. Usually, the ends of the stabilizer bar are connected to the left and right lower suspension arms. The center of the bar is mounted onto the frame, or part of the floor structure. When the left and right wheels move up and down the same amount in the same direction, torsion is not applied to the stabilizer, and resistance is not generated. But during cornering, the inside wheels will lose contact with the road surface, and the outside wheels will be pressed down. This causes the stabilizer to be twisted. The spring resistance generated reduces the leaning of the vehicle and keeps the body level. When soft springs are used in the suspension for maximizing riding comfort, or when independent suspension is used, leaning is especially severe during cornering. For this reason, this type of stabilizer bar is usually used on the front suspension. Sometimes, however, it is used on the rear. Suspension is divided into two types based on differences in their construction: rigid axle or independent. In rigid axle suspension, the left and right wheels are connected by one axle. The suspension is mounted onto the body via springs. The construction is simple and tough, but when one side of the vehicle goes over a bump, the vehicle as a whole is tilted. As the movements of the left and right wheels affect each other, shaking and jolting are made worse. An independent suspension allows the left and right wheels to move up and down independently. When one side of the wheel goes over a bump, the vehicle rolls less than that with rigid axle suspension. Independent suspension restricts the movement of the body and provides a comfortable ride and high steering stability, but its construction is rather complex. Now let's take a look at the types of rigid axle suspension. Leaf spring. In this type of suspension, leaf springs dampen the shocks received from the road surface. This suspension also functions as a suspension arm for holding the axle in place, which means that a linkage system to maintain proper positioning is not necessary. Its construction is simple but comparatively strong. For this reason, this type of suspension is used for buses and trucks. Coil springs are used in 4-link suspension. Springs cannot hold the axle in place with this type of suspension, so 2 linkages are provided on each of the left and right sides. The pair of lower control arms are long, while the other pair, the upper control arms, are short. They restrict the longitudinal movement of the axle. The lateral control rod provides lateral support. Here, the axle is positioned by a linkage, so soft springs can be used and riding comfort is good. Coil springs are also used in the trailing arm with twist beam type. In this type of suspension, left and right trailing arms restrict longitudinal movement by pulling the axle from the front. The lateral control rod provides lateral support. The construction of this type is simple and compact, and it makes for a soft, comfortable ride. It is used for the rear suspension of front-engine, front-wheel drive compact cars. Next, let's take a look at independent suspensions. A typical example is the double wishbone type, as explained earlier. A wishbone is the breastbone of a bird. An upper arm and a lower arm resembling this bone support a wheel in the longitudinal and lateral directions. This type is widely used for the front and rear suspensions of front-engine, rear-wheel drive vehicles. This McPherson strut type is widely used for the front suspension of front-engine, front-wheel drive vehicles. This suspension is called the strut type because the shock absorber also functions as the support for the suspension, especially when used for the front wheels. This suspension is called McPherson strut type after its designer. The upper end of the strut, incorporating the shock absorber, is mounted onto the body. The lower end and the steering knuckle, forming a unit, are mounted onto the body via the lower arm. The strut functions as part of the linkage and, along with the lower arm, provides longitudinal and lateral support. The strut is also allowed to rotate freely and functions as a kingpin. The characteristics of this type are the small number of components, each part having multiple functions, and its light weight. This suspension is considered suitable for compact, lightweight vehicles because of the small space taken up by the suspension. The suspension system plays an important role in enabling a vehicle to perform its basic actions, driving, turning, and stopping, and making the ride comfortable and the steering stable. This video has explained the construction and types of suspension system by taking typical systems as examples. There are many other types of suspension systems, and new types are being developed all the time. To improve your understanding of these systems, please obtain the latest information from Toyota Motor Corporation. For practical skill methods for suspension systems, please refer to this video's sequel, Suspension Systems Volume 2, Inspection and Maintenance.